once the webinar has finished. If in addition you also would like to receive a PDF copy of the slides shown, please kindly send an email to Wolfgang or myself. The email addresses will be displayed at the end of the webinar. As far as the webinar goes, we have an interactive part where we'll be asking 2 questions in the course of the webinar. In addition, you are more than welcome to ask any questions you may have using the Questions tab on the GoToWebinar app. The questions will be answered at the end of the webinar. If you have technical questions in between, due to skipping audio or whatever, you're also more than welcome to put those in the Questions tab, and I will try and see if I can solve them in the course of the webinar itself. Your presenter, as I said, is Wolfgang Radke from our facility in Mainz, Germany, and he runs the basically method development, or is head of the method development department, and is therefore excellently suited for giving you this course on liquid absorption chromatography. And I think with this I will actually hand over to Wolfgang. Wolfgang?
Yes, thank you very much, Derek, and hello to everybody at the other side of the ocean. Today I would like to give you a short introduction about interaction chromatography of polymers and how to select the right strategy for your separation problem. Oops. Okay. Just as an introduction, we have asked you in advance. We had a short survey where we asked how much experience do you have with chromatography of polymers, and that is the result that we have. So most of you have some experience with size exclusion or gel permeation chromatography. However, there is less users that have experience with HPLC on polymers, and that is what we are talking today. So, as you know, macromolecules are typically highly complex multi-component materials. If you have simply two monomers and you mix them together and do a polymerization, you can create a multitude of different structures. And with this multitude of different structures, you have also a multitude of different heterogeneities. What is most obvious is, what you know typically is that there is what we call a molar mass heterogeneity or molar mass distribution, meaning even if you start your polymerization all at the same time, you still in your final vessel you have always a mixture of chains which are different in lengths. So not all the chains have the same length, but they differ, and that is what we call molar mass heterogeneity or molar mass distribution. But if you have two monomers which you mix together in your vessel, then you will create chains of different composition as well. That means here in this example you might have purely blue chains, or you have red chains, or you have something in between. And this variation in the composition of the different chain in your polymer is what we call a chemical composition distribution. If you like, some people do that, you might create different architectures. You try to branch your polymers, you can create stars or something like that, and that might create chains which differ not only in molar mass, but also, for example, in the number of arms, in the number of branch points, and so forth, meaning what we have is a molecular architecture distribution. And finally, what you also might have is you would like to have chains which have different chain ends. For example, you might have functional groups at these chains, which you might use for further reaction, for example, cross-linking or chain extension. And that is very important that really your chains have all these functional groups that you would like to have. Otherwise, you cannot extend these chains, or you cannot cross-link. So but since not all chains might have the same number of chain ends by side reaction, you might lose one or the other functionality. We might end up with a functionality type distribution. All these heterogeneities, all these distributions will influence your application properties of your polymer, and therefore it is very important to understand what how the molecules look like. And what is shown here is that we have a mixture on two different samples, and if you look at the first glimpse, both samples look absolutely identical. You have the same composition, you have the same number of red and blue monomer units in both mixtures, and if you look carefully, you have the same number of polymer chains in each of these two samples, meaning the average molecular weight of both samples is identical and the average composition is identical. However, if you look closer, and that is what we have shown here, is that in fact the two samples differ. This here contains only this very nice grafted product. It's a completely homogeneous polymer, which you will never find in reality. And here you have blue chains, completely blue chains, you have red chains, and you have different graft products. Again, what you see here is you have a single technique, for example, NMR spectroscopy that you apply to these samples. You will see only the number of red and blue spheres, meaning you would not see a differentiation between these two samples. If you would only determine the average molecular weight, in that particular case the number average molecular weight, you would see no difference. Therefore, in order to really understand and find out what is the difference, you need to separate these polymers into the individual fractions to understand what is the sample about. Well, if we talk about separation of polymers, then most of you certainly know what we call size exclusion or gel permeation chromatography. What is that? In short, it's a liquid chromatographic technique where you have in this column, you have particles which have pores. It's a kind of a sponge, what you have, sponge-like particles. And if you introduce a sample which is composed of large and small molecules into this column, what will happen is, what is shown here on the right-hand side, because you have these pores, then your sample molecules, as they pass along these particles, have the chance to either go into the pore or not. And only those molecules, the small ones, which find enough pores, if the molecules are in the pores, they will stay there for a certain time before they come out and move forward. Since the small molecules have a larger amount of pores available because they can penetrate the large pores as well as the small ones, they lag behind because the large polymers can only penetrate the large pores, otherwise they wouldn't fit in. And in the result, what you end up is that as you pass through the column, the large molecules come out first from the column and give a peak into your detector, and after a while you will have the small molecules coming out last. So what we have is a separation based on the size of the polymer molecules. Well, this is a very simple example of size exclusion chromatography. Actually, it's a picture how it works. Is quite simple, but there is a certain limitation. As you can see here, all these molecules that I have drawn have the same size. But certainly this here is a different chain than that one, and here this functional polymer chain is different from this copolymer chain. Although they have these chains differ totally, you have a very highly branched molecule which have a different molar mass than the linear one, and so forth. All these molecules have identical size and would elute in a size exclusion experiment at the same elution volume. The reason is that the separation in size exclusion chromatography is based on the hydrodynamic volume. So that means size exclusion chromatography, gel permeation chromatography, is not capable to separate molecules of different topology and group of functionality or composition, which are of the same hydrodynamic volume. Therefore, in order to separate these kinds of molecules, for example, to determine whether I have molecules with and without a functional group, which is indicated by this yellow dot here, or whether you can separate a completely blue molecule from this copolymer molecule, we need other separation mechanisms beside size exclusion chromatography. So that means we need non-size-based separation techniques, and that means we would like to use interaction chromatography. Well, interaction chromatography is something you might know from your studies, from the classes, but most of the people have applied interaction chromatography to small molecules, and so we have to discuss different modes because the interaction chromatography almost differs to certain aspects from the interaction chromatography or HPLC of low molecules, of low molar mass molecules. What we'll discuss today is what we call isocratic adsorption chromatography. We will discuss something which is called critical chromatography and gradient chromatography. These are different modes where you can often find in literature where you can which you use to separate polymers. We will not discuss some other techniques, for example, temperature gradient interaction chromatography, TGIC, or we will also not discuss today barrier methods like liquid chromatography under limiting condition of desorption, or a similar technique which is called an SEC gradient, because these are separation modes which are less often used than the others, and we will stick today in this introductory part to the common technique and technical modes. If we talk about interaction chromatography, we first have to understand there is a separation based on the interaction with the stationary phase. And that is what you do if you also, what you have done in earlier times when you analyzed small molecules. However, there's a difference between large polymers and low molecular weight analytes. And as I said, it's especially this large molar mass which makes a difference. And the second thing which makes a difference is that we do not have only large molecules, but we also have molecular weight distribution or molar mass distribution. What is shown here on the right-hand side is a calculation where I have assumed that I have what we call a narrow distributed polymer, which has a polydispersity index of 1.1, and we assume that we have a number average degree of polymerization of 100. And if you look and you would like to pay attention to nearly all molecules, for example, just 95% of our molecules, then you will see in order to really look at look at all these molecules, you have to go down to the degree of polymerization from roughly 60 up to in the order of 140 or something like that. You find molecules of all different types of the chain lengths, 60 up to 140. So you have a large number of different chains which differs in their lengths. And here it's roughly in the order of 100 to 200, 100 different species which exist in your polymerization. And the question that we have to understand whether we are capable by interaction chromatography to separate according to something else than by molar mass, we have to understand how is a molar mass and molar mass influencing our separation. Because if there is a strong influence of molar mass, we might have co-elution again of different species of different composition, and that is what we don't want to have. But in order to understand how to get rid of this overlay with a molar mass distribution, we have to understand how is molar mass influencing our retention. So without going too much into a theory, sorry for that, I don't know what the reason is. Okay. We have to look first on isocratic adsorption chromatography. So how is a molar mass on polymer retention? And what we have to make a model, or we can use a very simple model to understand how this is working, or how the molar mass is influencing retention and isocratic absorption. We can first say, if I have a molecule running through my column, it might be either adsorbed, and then it's not migrating through the column, so it's sitting somewhere for a certain period of time, or it will be desorbed and can migrate, will be flushed forward with a solvent stream. So these are two states. And if we now have a macromolecule, then the macromolecule can only migrate if all repeating units are simultaneously desorbed. So that's very important. For a macromolecule to migrate through the columns, all our repeating units have to be desorbed simultaneously. And if you go to a little bit of the calculation, then you will recognize that the probability that all repeating units are simultaneously desorbed is quite low. Actually, it increases and will lead, even if we have a very low interaction of the repeating unit with the stationary phase, this results in very strong retention of the macromolecule. So the repeating unit itself is quite weakly adsorbed, but the macromolecule itself, because the probability that all repeating units are desorbed at the same time, for that the probability is quite low, and therefore we have to experience very long retention time for macromolecules. And secondly, it's not only long. What we can find out is that basically in isocratic adsorption chromatography, the retention increases exponentially with molar mass. It's not a single linear dependence, it's exponentially what's happening. As an example, we have shown here on the right-hand side the separation of polyethylene glycols on a C18 column, and you see you have different oligomers that you can separate. But as you can also see that the separation, the distance between two successive peaks become larger and larger. And if you go to higher and higher molar mass, then of course you will end up with quite long retention times. So that has something to do with the retention factor of the polymer. And typically, if you talk retention factor, that is defined as the retention factor is the time of the analyte to elute from the column, subtracting the time that the solvent needs to flow through the column, and divide it and then normalized basically to column length or to the retention time of the solvent. And typically, if you work with low molecular weight analytes and you do isocratic adsorption chromatography, then you try to reach retention factors somewhere between 2 and 20, I would say. Meaning, if you have 25 centimeter columns, you have retention times between somewhere in the order of 5 minutes to in the order of 40 minutes. That is what you would like to have. Within 1 hour, you would like to be done. However, that is what we have for low molecular weights. Now we can do some simple calculations. If we assume that our repeating unit, you could imagine I cut my polymer chain into small parts into the repeating units, and I would inject the single repeating units into the chromatography. And then you might end up with such a kind of chromatogram. This is my solvent peak, and these are 3 different eluent compositions. In one case, I reach for my isolated repeating unit a retention factor of 0.05, which means I have just 5% longer retention of the analytes and of the solvent. You have basically no separation between the polymer, between the repeating unit and the solvent peak, or I have here 20%, which is a little bit more. But still, these are numbers, interactions, which you usually do not like to have in isocratic HPLC. But although we have these tiny differences only in retention time, our in the retention time or in the interaction of the repeating units, our macromolecules will stay for a very long time on the column. As you can see here, for this example where the repeating unit is only by 5% longer adsorbed than the solvent, or is eluting only 5% after the solvent, you can see if you increase the chain length, the number of n here is the degree of polymerization. If you go to higher and higher degrees of polymerization, you rapidly end up at 100 minutes of retention time for the polymer itself, or for the polymer. If you go to even slightly higher retention time, you can see basically here you have for the repeating units 20% longer retention time on the column than for the solvent, but the polymer itself will basically not, or you will not be able to elute within a reasonable time degrees of polymerization higher than approximately 20. And that this is not only true in the calculation is shown here. Our PSG, again on this carbon 13, on the C18 column, and you can see how that really this exponential increase in retention time for the different composition of water methanol in our system is really obeyed. That means that you really end up with very long retention time for polymers. However, you might say, well, what's the problem? Yeah, the problem is the following. You have a molar mass distribution. Or you can say, and that is a problem. If you have, for example, a sample, again, it's a model calculation, having a dispersity of 2, again, number average molecular weight, and number average degree of polymerization of 100, you have this kind of molar mass distribution. If you now have this very weak adsorbing conditions, 5%, where the retention of the isolated repeating units is just 5% longer on the column than the solvent, then you will see that basically at a degree of polymerization, or what is it, 60 or so, you have already a very long retention. Even if you have a degree of polymerization of 60, your retention time is in the order of 100 milliliters. And if you go to and the other part of the major part of the molar mass distribution will elute even longer, and you will not see it from the column again. If you go to even slightly higher retentions of the repeating units, you basically have only a fraction of your molar mass distribution eluting under isocratic conditions from the column. So in isocratic adsorption chromatography, you have usually incomplete elution and reduced recovery, and that is not what you like to have, because you would like to know how your sample is looking about and not how a part of the sample is looking about. Well, you might say, well, the ugly sample from industries, let's have but I prepare something by anionic polarization, and so I have a narrow molar mass distribution. Well, that is not true. Here, just to give the comment, I even reduce the adsorption strength of the isolated repeating unit, and still I have the same problem. Even if I have basically no separation between the isolated repeating unit and the solvent peak, only under these conditions I'm able to fully elute my sample from the column. But if I have only 2% of stronger retention or later retention than the solvent peak, I always already have a very long retention. If I go to 3% longer retention time than the solvent, I have incomplete elution within 100 milliliters or 100 minutes elution time. So this problem of incomplete elution and reduced recovery is there irrespective whether I have a broad or narrow molar mass distribution. And that means isocratic chromatography of polymers under adsorbing conditions is only feasible for very low molar mass samples. And that makes the whole situation so difficult. So if isocratic chromatography under isocratic conditions is basically not possible, what we can do is something else. We can do what we call critical chromatography. LCCC, liquid chromatography under critical conditions. That means at this point we use a solvent, or to be more clear, we use an eluent where we have some size exclusion effect and some adsorptive effects. And at this critical conditions, the adsorption effect, which leads to the fact that that longer molecules would like to stay longer on the column, will be exactly balanced by the size exclusion effect, which comes from the pores. So we have a solvent somewhere in the middle between size exclusion and liquid adsorption chromatography. So under these conditions, if we select these very specific conditions for our polymer, then the retention becomes independent of molar mass. That is what you see here. Under certain conditions, you have no effect of molar mass of the polymer on the retention volume. So since the repeating units do not have an effect of the retention volume, we claim that the repeating units become chromatographically invisible. And that is a nice view how to understand what is going on in critical chromatography and how to use this mode of critical chromatography. It's not easy to establish, it's a lot of work, but you can use it for certain questions. And what questions can be answered with that? As told you, it's not easy to establish that, it's work. And so the question is, why should I put in a lot of work to find these conditions if I have no separation? Because what I show here is there is no separation according to molar mass anymore. But what we have is shown here. Let us assume we have these three molecules. A polymer molecule without functional group, monofunctional, and with two functional groups at the chain lengths. As I said before, if you do size exclusion chromatography, you will not be able to separate these polymers because they have of the same size. If you go to adsorption chromatography, most probably you will also get no separation because this little shift in retention due to the difference in adsorption strengths of the end group will be hidden by the molar mass distribution of the sample. However, if I now make my repeating units chromatographically invisible, meaning I select a certain solvent or a certain element such that the repeating units become invisible and do not contribute to the retention volume anymore, what my sample or my column sees only is this end group of the polymer. So if I have functional end groups, retention in liquid chromatography under critical conditions is determined only by the end group functionality. Another example or another way to use critical conditions, if you look at segmented polymers or on block copolymers. Again, I would like to know what is the molar mass distribution of this block on a block copolymer, for example. Again, I will not, in size exclusion or in adsorption mode, I have no way to look individually on this block. But if I use critical conditions, I make this block chromatographically invisible. And so my column sees only this deep blue block. So I have a way to look onto the block length of this visible block, although it is attached to the block copolymer. Another mode of chromatography is gradient chromatography. So what we do is, until now, we have used isocratic conditions. Now we start at a weak eluent. I inject my sample in a weak eluent, which leads to adsorption of the polymer chains to the stationary phase. And then I change my solvent during this chromatographic run. I increase eluent strength, and at a certain point, desorption might occur. Well, that will happen, and we have seen that critical chromatography is just at the border between size exclusion, where your polymer migrates faster through the column than your solvent, because that is the reason why in your size exclusion chromatogram you see this solvent peaks at the end of the chromatogram. And in isocratic adsorption, your polymer will elute later than the solvent peak. So the critical conditions correspond to the point where your polymer migrates through the column with the speed of the surrounding solvent, and that is the maximum speed that your polymer might have, because it cannot if you come from adsorption, you cannot run faster into the size exclusion mode, because that's not possible, because at a certain point your polymer migrates with the same velocity as the solvent and not faster, and so you cannot reach over into the size exclusion mode in gradient chromatography. So what happens is those polymers which have been sitting at the top of your column, small molecules will start a little bit earlier to move through the column because they are less adsorbed. But if I increase the solvent strength with the pump, then those molecules which are still at the column entry will experience this change in solvent strength or in eluent strength earlier than those molecules which have already started to move through the column. And the result is shown here in this slide. I told you all molecules have been adsorbed at the beginning of the gradient run, and these small molecules here started to migrate a little bit earlier than the other ones. Then the little bit larger ones start to migrate, but they experience better solvent conditions than this one, and so they migrate a little bit faster than the small ones. And finally, at a certain composition, the fat ones here will also start to migrate, but they are very close already to critical conditions near and will move much faster than the other ones. And for that reason, because the big molecules will catch up with the smaller ones, you will end up basically at the end of the column, say, in a linear gradient, all molecules will elute at the same time. That is shown here. Polyethylene glycols in a 90 minutes gradient, and what you see here is at low retention times you see these very nice oligomeric separations, And as you go to higher and higher retention times in this linear gradient, the peaks become get closer and closer together, and the peaks become sharper. And in the end, you will end up with a very sharp peak at very high elution volumes. If you plot that in a slightly different way, here is degree of polymerization versus retention time or retention volume. You see with increasing molar mass, the molar mass does not influence retention any longer. But at low molar masses, you might have an influence of molar mass on retention volume. Okay, that means in total we have 4 different modes of liquid chromatography that we have to look at. Size exclusion, the mode that you know. Liquid adsorption chromatography isocratically, which is basically not very convenient to use and it will probably lead to incomplete elution for your polymers. We have critical conditions, and we have gradient chromatography, and these are the different molar mass dependencies that we are looking at. These are the modes that we can look and that we can use to separate besides molar mass. So now we can ask, how can we use these modes to separate based on chemical differences? Well, in gradient chromatography, we have seen that high molar mass polymers elute independent of molar mass. At lower molar masses, roughly below, let's say, 30,000, you can observe some effect of molar mass. But we have seen that basically the transition from adsorption to desorption is governed or is identical to the critical point of the macromolecule. And that means in gradient chromatography of high molar mass polymers, elution is governed by the critical element composition. Since this critical element composition depends on the chemical structure, a PMMA has a different critical element composition on a silica stationary phase than a tertiary blue lacquerate, for example. The result is that in gradient chromatography allows separating high molar mass polymers of different chemical structure. We are able to separate based on chemistry high molar mass polymers. I just want to show you here that indeed the element composition at the time of elution of a certain polymer in a gradient is related to the critical conditions. What I have shown here is again our polyethylene glycols. If we increase the degree of polymerization, then we end up in a gradient at a certain retention time corresponding to a certain composition, in this case methanol water. Here, as you go to higher and higher molar masses, you end up somewhere, 82% of methanol in your solvent, and then you have no effect of molar mass. If we determine the critical conditions independently in isocratic experiments, then we obtain this line. So apparently the critical conditions are identical to the conditions where my polymer is eluting, high molar mass polymer is eluting in a gradient. The same is shown here for PMMAs. Again, if we increase the molar mass, we rapidly end up in a constant elution volume, and this constant elution volume is identical to the critical composition, which is shown here in dotted lines, that we have determined offline by isocratic experiments. So gradient chromatography is related to critical conditions. So, and now what happens now to statistical copolymers? Well, it has been shown by Yefim Brun, for example, that critical conditions exist also for statistical copolymers of a given composition. This critical composition depends on the copolymer composition, not only of the monomers, but it depends whether I have a polystyrene PMMA of 50-50 or of 48-42 composition. You have 2 different critical points for these polymers. And since in gradient chromatography, the elution is governed by critical element composition, that means by gradient chromatography, we are able to separate statistical copolymers according to the composition. That is shown here on this slide. This is an example of styrene ethyl acrylate copolymers, and you can see here, if you have a low amount of styrene, basically this is pure ethyl acrylate, you have an elution time of 15 minutes in this linear gradient that has been run. If you go to other compositions, you obtain larger and larger elution volumes or higher and higher amounts of THFs that you require in order to elute from the column, and you get a very nice separation according to chemical composition, which is not influenced any longer by the slope of the, or basically not influenced by the slope of the gradient, because it is the slope just shifts the critical point to a later time or to an earlier time, but since critical composition is a parameter determining the desorption of the polymer, the gradient slope should not have a strong effect. So now we have all our tools together, and we can ask ourselves, how can we separate homopolymers by functional end group? And actually, this is what you have to answer now.
Thank you, Wolfgang. So what we do in here is actually we will have you answer the question that Wolfgang just proposed. How can we separate homopolymers by functional end groups? Your choices are GPC-SEC, isocratic mode interaction chromatography, liquid chromatography under critical conditions, and gradient mode interaction chromatography. As always, the vote is completely anonymous, so you don't have to fear giving the wrong answer. And I would leave this vote open till we have a roughly representative result. So don't be shy. Pick what you think is the right answer, and we will be giving the results, and then obviously followed by the explanation and the right answer after the polls close. For all of you that are based in the US, this may actually be a test for the actual general election coming up, so tick your mark. I'm showing about 80% of the votes in, so I think I will close the polls right now and will display the results. So the results are 73% of you said liquid chromatography under critical conditions is how you can separate homopolymers by functional end groups, followed by 38% saying gradient mode interaction chromatography, 13% isocratic mode interaction chromatography, and 1% GPC-SEC. And obviously, the majority of you got it right. And Wolfgang, I'm going to hide this, and I will basically hand back over to Wolfgang, who will explain to you in more detail.
Yeah, thank you, Derek. Yeah, that is an example of liquid chromatography of a polybutyl terephthalate according to the number of end groups. And most of you have given the right answer. If I have a polymer where you have different end groups, but which have a broad molar mass distribution, I have to somehow mask the repeating units in order that they make no effect any longer on the retention volume. Otherwise, the effect of molar mass distribution will most probably overlay or mask the slightly stronger retention of the end groups. Some of you have argued with gradient chromatography and said, well, that can be done by gradient chromatography. Typically, you cannot separate by end groups. There might be very rare effects where you can do that if you have a very strongly retaining end group, but if you have basically no retention, if you have very strongly retaining end groups and you have no retention of the repeating units at all, that might happen, for example, if you have a polybutadiene or something like that with the large carboxylic end or with a strongly retaining carboxylic end. But normally, you will not be able to separate by end groups high molar mass polymers in a gradient. And also in isocratic mode, you will have the molar mass distribution. The effect of molar mass distribution will give rise to a very broad peak. And if there is a tiny shift by the end group, you will not see it. So the right answer, or the approach that I would like to choose, would be liquid chromatography under critical conditions. And here is an example, polybutyl terephthalate. And you see here, this has two alkyl groups that was in a polar stationary phase. a silica phase, as I remember. And if, again, these alkyl groups will not give rise to strong retention on such a polar stationary phase, if we make the repeating units invisible, then you end up here with the monofunctional OH group. This will give rise to additional retention, and that is the reason why this peak is shifted to longer retention volumes. And two OH groups will shift to even higher retention times, and you get a very nice separation of by the number of OH functionalities in this kind of system. Keep in mind, these peaks look so narrow, not because they are monodispersed with respect to molecular weight, but because we have eliminated the effect of molar mass. Below each peak, you have a complete molar mass distribution, having roughly a polydispersity of 2 or so, as we have typically find in such polycondensates. Another example on how to separate, or that is possible to separate by liquid chromatography by the factorized ends group, is shown here. What has been done here was a separation of polylactide stars, and each of these stars has at its arm end an OH functionality. What has been done first in this investigation, which has been performed in the group of Harald Pasch, is first the critical conditions have been established for polylactides, meaning without any end group, and under these conditions, a linear polylactide has no effect of molar mass. All linear polymer chains have eluted at the same elution volume. This one-arm star, for example, and because the end group do not contribute under these conditions. But if you have established critical conditions for linear chain, and then you add up more and more of the OH groups, which give rise to additional retention, you can see that with each additional OH group, you will increase retention. And that is a very interesting result, because if you like to use such molecules, for example, as cross-linker, then the one-armed star, or the linear polymer, is of no help, because that will not give rise to cross-linking. It will terminate your polymerization reaction. This two-armed star, how I call it, will only give rise to a linear polycondensation, but it will not cross-link. And so you have to know what is the amount of material which actually can lead to cross-links. So indeed, the mode of separation for end group functionalization is critical chromatography. Now let's ask, how can we separate by stereochemical composition? But that is a broad field, and I would like to ask the question, how would you like to separate a polymer blend? Again, so I hand over to Derek.
So that's me giving you again the chance to vote. And there we go. So the question, as Wolfgang proposed, how can we separate polymer blends by chemical composition? GPC-SEC, isocratic mode interaction chromatography, liquid chromatography under critical conditions, or gradient mode interaction chromatography. Those are your choices. And I'm going to leave the polls open again till we have about 80% of you who voted, so that we kind of get a representative overview of what you think is the right approach. Again, how can we separate blends by chemical composition? GPC-SEC, isocratic mode interaction chromatography, liquid chromatography under critical conditions, gradient mode interaction chromatography. You're getting good at this. We're already at the 80% mark. So I'm going to close the poll, and I'm going to share the results with you. Oops. There we go. So almost 80% of you answered gradient mode interaction chromatography, 25% liquid chromatography under critical conditions, 15% isocratic mode, and 2% GPC-SEC. And to find out what's actually right, I'm going to hand over to Wolfgang again.
Okay, thank you very much. Thanks, Derek. Yes, actually, most of you have been correct. The method of choice, to my understanding, is to separate polymer blends is gradient chromatography. in a blend, you have two polymers which have different critical compositions. Critical composition is responsible for the elution time in a gradient, and therefore you should be able to separate blend in a gradient. We will also discuss quickly later on the critical mode. Again, isocratic adsorption chromatography seems to be not feasible because high molar mass polymers will simply not elute completely in isocratic mode. Size exclusion, well, if you're lucky and you have really a blend composed of molecules of two components which differ extremely in their molar mass, you might be able to do that. But to my understanding, the selection of choice is gradient chromatography. Here it's shown an example, a blend or a mix, and actually it was not a mixture, it was individual components. But you can see here in this gradient running from what I guess it was, and that was Mubashir Bashir, so it must be a toluene to THF. On a silica-based column, on a silica column, you see the PMMAs elute at a quite high amount of THF. Again, you see the slightly lower molar mass PMMA elutes a little bit earlier because of some tiny effect of molar mass, which vanishes then somewhere here in this region. But the N-butyl acrylate and the T-butyl acrylate elute much earlier, but because they are very similar polarity, they are quite close to each other. However, there have been 25% of you who said, well, there might be liquid chromatography under critical condition might also be helpful. And indeed, this is the case. That is an example, again, from the group of Harald Pasch, and that was blends of PMMA and polydecyl methacrylate. And what has been done here is this guy selected critical conditions for polydecyl methacrylate, as you can see here. The decyl methacrylate, irrespective of the molar mass, elutes all at the same time, while the PMMAs elutes earlier, or the PMMA elute earlier on this column combination. It was a non-polar column, THF acetonitrile mixture, and you can see here the PMMA elution is not influenced by the molar mass of the PDMA. But what you can see here as well is the higher the molar mass of the PMMA, the earlier it elutes. And that is a benefit of this approach. While in gradient chromatography, you might get two peaks for the decyl methacrylate and the PMMA. So you can quantify the amounts of both components. By critical chromatography, the benefit is that you can obtain the molar mass distribution of the non-critical blend component, meaning under these conditions, under the critical conditions of the polydecyl methacrylate, I can do a calibration with PMMA. And if I have my real blend, then I can use this calibration with PMMA to determine the molar mass distribution of of the unknown PMMA within this blend. And therefore, both answers, gradient chromatography and critical chromatography, are equally right, depending exactly what you would like to learn on your sample. How can you separate statistical copolymers, or mainly block copolymers? I don't want to bother you with going into questions again. That is something we can do with block copolymers. I told you that critical chromatography on block copolymers can be used to determine the length of a single block attached to block copolymers. How we can do that? Again, an example from Jana Falkenhagen in Berlin. And what she did is she investigated PMMA, block copolymers of PMMA and tertiary butyl methacrylate. And at critical conditions of the PMMA, which is now shown in blue, and what you see is you have these kinds of molecules. She had block length of the TPMA was identical, and the length of the PMMA block was different. And under the critical conditions of the PMMA, critical conditions means we make the blue block invisible as indicated here. You see that indeed all three samples, although the molar masses of the PMMA are different, eluted at the same time. So apparently under these critical conditions, the PMMA block, the invisible block, does not influence the retention of the block copolymer any longer. And again, we could now make a calibration with homopolytertiary butyl methacrylate and could calculate the molar mass distribution of the block copolymer of the TPMA, which is attached to this blue PMMA chains. If we turn the system around, and we have now chains where we have different lengths of the tertiary butyl methacrylate, again under critical conditions of the PMMA, then of course the PMMA will still not give rise to any effect of molar mass, and you can see that now we have here PMMA and the pure PMMA and some residual PMMA from the synthesis, but most importantly, most interestingly, the length of the T-butyl methacrylate block influences now retention. So the PMMA block does not influence retention, as we have seen on the last slide, but the T-butyl methacrylate influences retention, and that is a way to determine the block length of the PTMA block in such a block copolymer. That means liquid chromatography under critical condition allows estimation of the block lengths in block copolymers. And I always write here estimation because, well, there have been under certain conditions also you might see a tiny effect of the non-visible block as well. That is still ongoing discussion, but at least you get a better insight into the block length of the block copolymer in these molecules. How can we separate statistical copolymers? Well, here's an example from my side. I was using recently separate lactide glycolide copolymers, PLGAs, by composition. And as you can see here, the PLGA having a large amount of lactide in it elutes quite early in a very sharp peak. And with decreasing amount of lactide, increasing amount of glycolide, you shift the peaks to higher and higher retention volumes. And if you do that with such a kind of copolymer, then you can basically calibrate your axis. If you have samples of known composition, you can calibrate your retention time axis, and you can determine the chemical heterogeneity of such a distribution. And you see here, for example, this lactide has a much broader heterogeneity than this 85% lactide containing sample, which is obvious because if you go to the 100%, you have no heterogeneity at all. If you have 100% lactide, it's a PLA. There is no chemical heterogeneity. It must be actually a very sharp peak. If you go to 100% polyglycolide, it is also a homopolymer, has no heterogeneity with respect to composition, should also elute as a quite sharp peak, while in the intermediate range you will have copolymers, even the average composition might be 50% lactide. You will certainly have chains which have, for example, here 55 to 60% lactide, and you go up to down to what it might be 40%, 35% lactide on the other end. So here in the copolymer you have heterogeneity, in the homopolymers not, and then it's quite obvious that the peaks should become broader in the intermediate compositions than at the edges where you have the homopolymers. Well, you might ask, wouldn't it be a way to use liquid chromatography under critical conditions to separate statistical copolymers? And here is the answer. To my understanding, it's not possible. Why? Well, if you have statistical copolymers and you would like to establish for one composition, that is this green, this might be composition number 4, for example, you establish these critical conditions, then the other compositions are either a little bit stronger or a little bit less adsorbed to the stationary phase, meaning the other compositions are either eluding in liquid adsorption mode or in size exclusion mode, giving rise to molar mass dependencies again. And therefore, if you now, under these conditions, look at this elution volume, you have a co-elution of different compositions with different molar masses, meaning we have co-elution again, and we cannot separate by statistical copolymers by critical chromatography. Let us quickly talk a little bit about practical considerations. What is required to perform either critical conditions or gradient chromatography, the modes that we were talking today? Well, if you look at GPC, you are happy, you need just an isocratic pump, and that's sufficient. If you go to interaction chromatography, an isocratic pump might be sufficient if you run critical conditions, but we have seen that you are very limited, and most of the time you would like to use a gradient pump in order to really achieve a separation of a large range of different adsorption strengths of the polymer. Then we have to talk about a column thermostat and column oven. In GPC, that is usually not required. In GPC, the column oven is only required to reduce solvent viscosity and to increase the mass transfer and thereby narrowing the peaks. However, in interaction chromatography, the retention is strongly temperature dependent, and therefore it's required that you really maintain a constant temperature in order to repeat your experiments. So a column oven is required in interaction chromatography. So mobile phase, well, in GPC, you have a thermodynamically good solvent, isocratic. In interaction chromatography, again, you should use a good solvent. Very often, people try to use weak solvents in order to establish adsorption effects. Then you do not make interaction chromatography. You're running more into precipitation redissolution adsorption chromatography, which complicates the interpretation of these values. So for a gradient, you need at the beginning a weak element, meaning a solvent which allows your polymer to become adsorbed to the stationary phase. And then you add another solvent to your mobile phase, which is capable to reduce the adsorption strength of the adsorption of the polymer. So you need actually two good solvents, one weak one and a strong one. In critical chromatography, you have also mostly a solvent mixture, but should also be a good solvent for your polymer. Columns, well, in GPC, you have most of the time you run polymer-based columns, and sometimes you use silica. In interaction chromatography, it's the other way around. Most of the columns that are used in interaction chromatography are still silica columns. Usually we can classify it as polar columns, which are used for normal phase, or unpolar columns, which are used for reversed phase applications. Detection, since GPC you run only isocratically, the refractive index is suitable. However, in interaction chromatography, it's much more common to use UV or DAD detection if you have chromophores in your polymer, and provided that your solvent has a free window where you can use UV detection. Most of the time, the ELSD, the evaporative light scattering detector, is a method of choice to run gradient chromatography or critical chromatography. I would like to come to the conclusion. To my understanding, the main features of polymer chromatography are qualitatively well understood. Upon selecting the right chromatographic strategy, you can separate by different structural features. And if you have such a separation which is not based on size, you might also be able to use this illusion mode and to couple it to a two-dimensional separation where you can separate, for example, in terms of chemical composition in the first run, and then later on by size. Each fraction can be separated by size in a separate separation. With that, I would like to make a little bit of an announcement. We have recognized that we have today a very large number of attendees, and we have also recognized over the last years that there seems to be an increasing interest in interaction chromatography of polymers, and that has led to the conclusion that PSS is offering in 4 weeks' time a one-day classroom-style training on liquid interaction chromatography of polymers in Mainz. Unfortunately, the language will be German. We would like to see whether there is enough interest to create such a course and to offer it. if you are interested in general in other countries or in the English speaking courses, please contact your PSS representative. And with that, I would like to thank you for your attention.
Thank you, Wolfgang, for the very interesting presentation. We do have a couple of questions. Unfortunately, we only have little time. So let me first do the usual. I think you may still have a slide with our email addresses. If not, I will send them out via the chat message so that people can request a copy. There we go, a copy of the PDF. So if you would like to have a PDF of the slides, either send an email to myself or to Wolfgang. That also goes obviously for all the people who in the US may be interested in the classroom style training that Wolfgang just mentioned for liquid absorption chromatography. Send an email to myself so I can try and see if we can make this a feasible option here in the US as well. To the questions. There's one question you mentioned in the beginning when you talked about isocratic chromatography. You mentioned very low molar mass where isocratic chromatography is feasible, for example, for polyethylene glycols. What molar mass would you consider very low molar mass with respect to that, where isocratic chromatography would actually work?
Actually, if you look at it, you cannot simply say there is a number, because the problem is if you decrease the adsorption strength, you can go to higher molar masses, but you lose the separation on the low molar mass, and because it comes very close, the low molar masses come very close to the solvent peak, and so you have no retention of the low molar masses, but therefore you might be able to elute the higher molar masses. So it depends very much on the width of the polydispersity of your sample. Actually, I would say maybe in the order of degree of polymerization 20 or so. As we have seen before, we had this very nice separation in a gradient where we have much better separation by gradient chromatography. So in principle, I'm not a fan of isocratic adsorption chromatography because if you would like to elute higher molar masses in a reasonable time, your adsorption strength of the repeating units is so weak that the tiniest change in eluent composition creates problems.
Thank you. Then I have two questions regarding liquid chromatography under critical conditions, which I would like and try to combine. Question number one is, how do we make the chain invisible? And number two is where it is. They keep popping up so fast, I have to apologize. Well, let's start with that, and I'll get to the other one.
Yeah. Unfortunately, I had no time within this 1 hour. We cannot go through the whole course that we are offering in Germany for a whole day. Actually, what you do in critical chromatography, basically you have seen this fan-like picture where we have size exclusion, liquid adsorption, and critical conditions. All can be done on the same column. I love my example is PMMA on a silica column. PMMA on a silica column in THF gives a very nice GPC-like illusion, meaning high molar mass comes out first, low molar mass comes out last. If you go to chloroform or tolu, you will not see your high molar mass PMMAs anymore. It will stick forever on the column. And actually what you have to do is now, you have to play now around with the composition of your strong solvent, which makes size exclusion, or in which your polymer makes size exclusion, I have to say, and with the amount of the weak eluent, which gives rise to adsorption. And then you basically inject at different eluent compositions, and you look whether I see that the high molar mass comes out first or whether the high molar mass comes out last. And then you have to play around with the solvent compositions. That's actually what you have to do. It's a lot of work. To get a first estimate of where your critical composition might be, I usually like to run a gradient first. I have shown you that in a gradient, the eluent composition at the time of elution is very close, at least, to the critical conditions. So if I run a gradient and now know my 12 volume and so forth of my instrument and my column volume, I can calculate that at 5 milliliters in retention time, I have a composition of THF and chloroform of 60%. And that is always a good starting point, at least, to then start really doing actually to establish the critical composition. So then you have really to go into this trial and error procedure. Another comment, the fact that you have established critical condition does not automatically mean that you get a separation by end group functionality. Keep in mind, you can only expect a separation by end group functionality, for example, if your end groups are stronger adsorbed than the repeating units. So you really have to think about what is my stationary phase look, how to select the stationary phase according to the problems that you are investigating. I hope this answer gives you, this answer helps you a little bit at least.
It actually answered the second question that I now found, which is what is the best approach to establish critical conditions? You touched that as well. So basically, wonderful job of anticipating my second question. One other question we have, and I know we're rapidly running out of time and people are leaving. So when you leave and have to go, there will be a sort of exit poll in the end where you can tell us what you liked about the webinar and what you didn't. And I would like to invite all of you to actually take that to make this webinar better for you. One last question, I think, is when performing adsorption chromatography, and that probably is important for all people who usually do SEC and now have a first glimpse at liquid absorption chromatography, is the pore size of the column material still of importance?
Yes, depending on what you would like to do. I have to say there is not... Well, it depends on what you like to do. First of all, what is known is the smaller the pore size, the more difficult it is to establish critical conditions. First point. So that would mean I would like to use larger pore sizes, then I don't run into so much trouble. If the molecules are large as compared to the pore size, then tiny effects in solvent composition have stronger effects on retention volumes. To my understanding, this means if I would like to separate by end group functionality, it seems to me more easy to do that in large pore sizes. If you, however, would like to investigate, for example, the blend or the LACforPolymer and would like to determine the molar mass distribution, or you would like to separate the blend by critical conditions, then you have to make sure that your visible blend component is shifted far enough from the invisible component. The invisible component will elute very close to your solvent molecules. In that particular case, small pore sizes would be attractive because if the small pore size should get a very good separation between the visible polymer and the solvent region where your invisible polymer should elute. So that is, again, you have to think about these facts as well.
Okay, thank you, Wolfgang. And I think with this, there's still a couple of open questions, but I think we will just rather answer them via email. If you have additional questions after either going through the slides or looking at the recording, which will be available roughly in about 24 hours' time, you're more than welcome to send us an email, and we're more than happy to help you out. So with this, I would like to thank Wolfgang for this nice presentation and all of you for attending wherever in the world you may actually have listened to this. So good morning, good afternoon, and good night from Amherst, Massachusetts. And I'm going to leave the famous last words to Wolfgang.
Yeah, again, also from my side, for you in Europe, have a nice evening. Thank you very much for attending. I hope it was interesting. And for those of you who still have to work, I hope you have a good working day. Bye-bye.